Hello and welcome you all to the second lecture on the standard model of particle physics, where we are actually discussing the electroweak interactions within the standard model. In the first lecture, we actually talked about briefly that what constitutes the standard model. Basically, we talked about the particles, its properties in a brief, and then we talked about the kind of interact within the visible sector. Now, in this lecture, we are going to talk about something very important, which is actually about the special relativity and Lorentz transformation. Okay? So, let us get started. Special relativity is required because I told you in the last class that when we are going to talk about the fundamental particles which are moving very fast, then not only quantum mechanics is required, but what we require is to also the special theory of relativity, because the classical domain is no more applicable. So, we need a marriage of quantum physics with special relativity, which actually gives rise to what we call the quantum field theory. So, therefore, we require the special relativity to start with. Now, the basis of this is to look into two different coordinate system, one which I call x, y, z, or the S frame, so to say, and the other frame that I am talking about is called S bar frame, in which the coordinates are x bar, y bar and z bar. And what I am having is that I am assuming that this S bar frame is moving with a velocity v along the plus x direction, and the v is sufficiently large. And so, therefore, the space time points, if you want to say, for the coordinate s, or rather S frame, is described by x, y, z, t, whereas for the S bar frame, the coordinates are described by x bar, y bar, z bar and t bar. Okay? Now, the main point of the theory of relativity is essentially the fact that we need to sort of adhere to the fact that the velocity of light remains constant in all inertial frames. Now, this was actually a realization which was actually obtained in order to keep the Maxwell's equations, or so called wave equations associated with the electromagnetic fields, intact in all different inertial frames. People soon realized that if you change the velocity of light from one frame to the other, like if you are adding something like c plus v or c minus v instead of having the velocity of light to be c, the equations actually are changing in different frames. So, therefore, they were kind of skeptical if this is really happening. And then you know this famous story of Michelson-Morley experiment, which tried to measure the velocity of light in different moving frames, and it actually saw that it is not changing. So, therefore, one of the main interpretation of special theory of relativity is that the velocity of light remains constant. So, this is what I am going to write once: velocity of light remains constant in all inertial frames. Now, therefore, you can simply say that if that is the case, then x squared plus y squared plus z squared must be equal to c squared t squared, which is true for the S frame, whereas for the S bar frame, I must write this relation as x bar square plus y bar square plus z bar square equal to c square t bar square, correct? Or in a other way around, we can say that the space time intervals are actually kept constant, that is c square t square minus x square minus y square minus z square must be equal to c square t bar square minus x bar square minus y bar square minus z bar square. The question will be that what is the transformation that will take you to x, y, z, t to x bar, y bar, z bar, t bar, so that this c square t square minus x square minus y square minus z square is equal to c square t bar square minus x bar square minus y bar square minus z bar square. What is the transformation? And it turns out the transformation looks like this, that if you write x bar equal to gamma into x minus Vt, t bar equal to gamma into t minus Vx by c squared, and y bar equal to y and z bar equal to z, caveat to the fact that when this s bar is moving along the positive x direction, then this transformation, this set of transformations will actually keep that space time intervals constant or the same. Okay. What is the definition of gamma? The gamma is essentially defined by 1 minus beta square whole to the power minus half. What is beta? Beta is essentially v by c, the ratio of the velocity with respect to the velocity of light. Now, in h cross equal to c equal to 1 unit, which we just talked about, the natural units, we often drop c. So, the gamma will be essentially 1 by square root of 1 minus v square by c square. This simply turns out to be 1 by square root of 1 minus v square. Now, if we adhere to this h cross equal to c equal to 1 unit, then you can see that this x bar can be written as gamma into x minus, instead of v, I can simply write beta into t, correct. The second relation will be gamma into t minus beta into x, because I have chosen c equal to 1, and so therefore, the beta is nothing but v itself. So, this is how I can actually describe the transformation. Now, the question is, what are these transformations called? And many of you already know that these are called the famous Lorentz transformation. So, these are the transformation which will actually takes you from one coordinate system to another inertial coordinate system. Okay. From one coordinate system to the other, which is moving with a velocity v. Now, this is specific when the motion is along the plus x direction. You can rewrite this easily for other cases, like if it is moving along plus y plus z or etc., or even along a diagonal direction also. And it is very easy that to check that these transformations indeed keep this space time invariance constant in different inertial frame. I suggest you that you must actually do check them. Now, if I now want to write this transformation in a matrix form, how will they look like? So, for example, you remember that I wanted to write this in the t x y z 1. So, what I did that I actually essentially wrote the space time points in terms of a Coulomb matrix. So, I have a t x y z, the coordinate and time space time coordinates on the right hand side here. On the left hand side, I essentially have the space time points for the s bar frame, which is also written in terms of a column matrix, which is t bar, x bar, y bar, z bar. And then I wanted to write in the matrix form what exactly is the transformation which takes you from s to s bar. So, you see, then this matrix will be following this notation that I just devised. You can clearly see that these inputs will be gamma minus beta gamma. Here we have minus beta gamma and gamma. So, if you do this matrix multiplication, you can simply see that we can find out this relation like t bar equal to gamma into t minus beta gamma into x, and the other components are completely 0. So, we basically retrieve this transformation by this matrix form, and this matrix form is what we call, in a component notation, we write it like lambda mu nu matrix. Now, this equation is the same way of writing this matrix equation in terms of components. So, for example, if I devise this notation that x bar mu, where mu takes the value from 0, 1, 2, 3, which corresponds to time and 3 space points, then this x bar mu can be related to lambda mu nu x nu. Now, you see that this nu index is repeated and summed over. This is what is called the Einstein's convention. Suppose you want to write x bar 0. How you will write it? X bar 0 will be lambda 0 0 x 0 plus lambda 0 1 x 1 plus lambda 0 2 x 2 plus lambda 0 3 x 3. So, nu will be repeated and summed over. So, this is what we called that Einstein's summation convention, and these two indices are repeated, and you see that one is in the superscript and one is in the subscript, and that is a necessity condition for them to be repeated and summed over. So, this is how we are writing it. Or in other way, we can say that the definition of this lambda mu nu, which essentially depicts this 4 cross 4 matrix, the Lorentz transformation matrix that we just talked about, that is defined by del x bar mu by del x nu, and this is what we define as a Lorentz transformation matrix in component form. Now, what will be the different components of this Lorentz transformation matrix? For example, lambda 0 0 lambda 1 1, ye kya hoga? So, this is from the very definition of this matrix, if we look into, this will be simply gamma, correct? What will be lambda 1 0 and lambda 0 1? You see that both of them are once again equal, and this will be nothing but minus beta gamma. What will be lambda 2 2 and lambda 3 3? These are nothing but 1, and all the other components are 0. So, this is precisely what defines the Lorentz transformation, which takes you from one inertial frame to the other inertial frame, and this is the component notation which we are going to use. Now, why this transformation is required? Now, we say that a good physical theory requires quantities that are Lorentz covariant. That means it transforms appropriately with the Lorentz transformation. What do I mean? What I mean is that we can have objects which are called the scalars under Lorentz transformation. That means the quantities which are numbers and which are called Lorentz invariant quantities, and these are not changing under this transformation at all. So, these are classified as scalars. For example, a scalar field, whenever you have a number, that will not depend on the coordinate system that you are measuring. It only depends when you have to assign a basis for that, right? And that is precisely what we define as vectors. So, any vector will actually have a transformation, and so therefore, if that transformation can be similar to the coordinate transformation, like x mu going to x bar mu. Now, there are two different kinds of vectors that we can define, and the first kind that we are going to talk about is a kind where the index is actually written in the superscript, and that is what we are writing, like a mu is going to a bar mu when you are going from S to S bar frame. Now, how do I write in terms of the coordinate transformation? Remember, this a bar mu is a vector which is defined in the S bar frame, which is actually defined by x bar mu coordinates. So, then I can write this as del x bar mu del x nu into a nu. So, once again you observe here that this nu is a repeated index which is actually summed over, and we have del x bar mu del x nu. Now, can you remember that what this del x bar mu del x nu matrix is? You can go back and take a look into this definition. This is nothing but the Lorentz transformation matrix itself. So, this is lambda mu nu a nu. So, therefore, there is a kind of vector which exactly transforms as the coordinate transformation. So, this is exactly how the coordinate transforms, x bar mu goes to lambda mu nu x nu, and this is what are called contravariant vectors. So, this is what is classified as contravariant vector. One example is the momentum. If you look into the momentum, it exactly transforms as a contravariant vector, like p bar mu is lambda mu nu p nu, where lambda mu nu is essentially the Lorentz transformation matrix. What is p mu? This is the 4 momenta. The inputs of this 4 momenta are essentially the energy as the first component and the 3 momenta as the last 3 components, px, py, pz. Now, this is not the only kind of vector that we can think of. There is also other kind of vectors that we may have, and this is what are called covariant vectors. For example, if I now write a vector with a mu index sitting at the subscript like b mu. So, if it transforms to b bar mu, then how can we write the transformation? Remember, the coordinate transformation, the coordinate indices are always sitting above. So, this mu which is sitting below has to be adjusted something under the derivative, right. So, we can say that this might be described by del x nu del x bar mu. You see this del x bar mu with mu an index which is sitting as a superscript to x, but the whole term is actually under the derivative. So, this justified the covariant index which is the free index of this equation, right. So, b bar mu with the covariant mu is adjusted with a x bar mu or del x bar mu sitting in the derivative in the denominator essentially. Now, this nu that we have is essentially a repeated index and it must be a dummy index. So, this has to be summed over. So, we will say this is del x nu del x bar mu b nu. So, you see that this index is repeated and summed over. Okay. Once again the same way that we actually defined this one. But now interestingly, if you look into this transformation matrix, this is not exactly the same as Lorentz transformation, and so this is called covariant vector, and this is a little different from what we have for the contravariant ones. Now, from the terminology, it might be a little kind of intriguing that anything which covaries should be called covariant vector, anything which contravaries should be contravariant vector. Now, the one where we have the vectors transforming exactly as Lorentz transformation or coordinate transformation, we called that to be a contravariant vector. So, it contravaries what? It contravaries the basis. And on the other hand, this example that I talked about where b subscript mu going to b bar mu having a transformation not exactly as Lorentz transformation, but it covaries with what? Why shall it be called covariant vector? The point is the basis vector actually transforms as Lorentz transformation in these cases. So, the transformation of the basis vectors and the coordinate vectors are actually different. So, the terms that we have introduced are basically based on that. So, can we take an example? For example, we can look into this object like del phi del x mu. It is a derivative of a scalar field with respect to the coordinate system. Now, if I have to write the transformed one for phi, phi does not change because it is a scalar field, right, it does not depend on the coordinate system. So, del phi del x mu will change to something like del phi del x bar mu. Now, how do I write this? This del phi del x bar mu should be written as del x nu by del x bar mu del phi del x nu. So, this index is missing. So, once again you see that once again I would like to draw your attention that this mu is a free index on both sides of this equation. Okay. This nu on the other hand is a repeated and dummy index which is summed over. Okay. So, if I had to write something like del phi del x bar alpha, then I had nothing to choose for del x bar alpha on the right hand side of this equation because that is the free index which I am having. For repeated index I can take anything. You do not write this terminology nu, you can write it beta, you can write it gamma, whatever that you want, right. So, for example, here instead of writing nu, there is nothing specific about nu here. So, I can also very well write say for example gamma or alpha, say for example, I can write alpha for both these cases. It does not really matter because it is a repeated one and summed over. So, the point is there are two definitions that we actually have to come across. One which is called the fourth derivative, which is defined as del mu. This is also written as del x mu. Now, what does it constitute with? This has four different components as we can imagine. The first is the derivative with respect to time, which is del t. The other three are del x, del y and del z. And similarly, what I can do that I can define a double derivative which I call del mu del mu. Now, you see interestingly that there is no index left. Here also this indices mu and mu are repeated and summed over, okay, and this gives you what you call a box operator and which is also called a D'Alembertian operator, okay, and this is defined as del 2 del t2, del 2 del x2, del 2 del y2 minus del 2 del z2, okay. So, this is the definition of the box or the D'Alembertian operator, and this is nothing but del 2 del t2 minus del 2 del x2 minus del 2 del y2 minus del 2 del z2. There is one important point which we would like to now come to, is that the norm of a vector is always a scalar, and that remains invariant under the Lorentz transformation. So, what is the definition of a norm of a vector? So, x bar square is defined as x0 square minus x1 square minus x2 square minus x3 square. Importantly, this can also be defined in terms of a metric tensor like g mu nu, x mu, x nu. Or you can say that this mod of x square is something like x contravariant mu, x covariant mu, okay, where these mu indices are repeated and summed over. Now, this x mu is obtained by this operation g mu nu, x mu, x nu. So, in a sense you can say that this x covariant mu is obtained by g mu nu, which essentially g mu nu x nu. So, you see this nu is now the repeated index which is repeated and summed over, and in the process you have a free index left which is bringing the contravariant component or the contravariant index to a covariant one. So, you can define a covariant coordinate with respect to this metric tensor g mu nu. Now, if this definition, so therefore, what this will be? This will be simply t square minus x square minus y square minus z square, right. So, x0 square is t square, x1 square is x square, x2 square is y square and x3 square is z square. So, mod of x square is simply t square minus x square minus y square minus z square. Now, once again, if you are trying to write this in terms of a metric, how do I write it? I will actually write it in terms of a 4 cross 4 metric, and in this 4 cross 4 metric, how it will read? It will read like 1 minus 1 minus 1 minus 1 in the diagonal entry and 0 everywhere. So, this is once again following this definition that your ds square or x bar square or mod x square equal to g mu nu x mu x nu. Okay. And this also is called the Minkowski tensor, which sort of defines the flat space time. Now, you can say, okay, this is actually in the Cartesian coordinate system. Say for example, I want to define the motion of a particle in the spherical polar coordinate system, or rather polar coordinates in the 2 dimension. Then in that case, how do I define this metric tensor? That is a legitimate question, right. So, let us first try to write what you call the ds square in that case, and we all know that in this particular case ds square is defined by dr square plus r square d theta square, right. And in this case what you have that grr, therefore, the component which actually precedes the dr square is what I call grr, that will be equal to 1, and what will be the component for g theta theta? That will be simply r square, right. So, let us then try to write this g mu nu, or in that sense you can say that this ds square is nothing but g mu nu dx mu ds nu. Okay. So, what will be the g mu nu matrix? Let us try to write it explicitly. As you can imagine that now this will be a 2 cross 2 matrix, right. It has basically described 2 of this coordinate system r and theta. So, in this 2 cross 2 matrix, what shall we write? grr is equal to 1, gr theta is equal to 0, g theta r is once again 0, and g theta theta is equal to r square. So, this is actually the g mu nu matrix, which actually describes the motion of in spherical or rather polar coordinates in 2 dimensional motion. You can actually extend this idea to write the g mu nu for the spherical polar coordinates in 3D. You can write it in the cylindrical coordinates, and you can do numerous exercise, and I suggest that you do that actually for these different cases. Okay. The important point which we borrow from this whole thing is that for any vector, when we actually define the norm, it is a scalar. So, basically we can define a square which is nothing but the multiplication of the contravariant and the covariant components with the repeated indices, which we can simply write as g mu nu mu, and that will have this a0 square minus a1 square minus a2 square minus a3 square, and because it does not have any indices left, so it is a scalar. it does not transform under the Lorentz transformation. So, the norm of any vector is always a scalar. Depending on what kind of values it can obtain, it is classified in different categories. For example, if a square is equal to x square is greater than 0, then this mu is called a time-like vector. If a square is less than 0, this is called a space-like vector. If a square is equal to 0, it is called a light-like vector. Now, I would like to urge you to go back and do a little bit of search on why these specific names are assigned for these different conditions, which I am not going to tell you right now. Now, it is not only the norm of a vector, but also if you take an inner product of two vectors, that is also Lorentz invariant. For example, I can always define an A dot B, which is equivalent of doing A mu B mu, right, and this will be simply A 0 B 0 minus A dot B, and that is nothing but G mu nu A mu B nu, right. So, therefore, we can always define an inner product with the two vector, which is also a Lorentz invariant or a scalar basically. So, these are example. So, I will take another example. For example, the inner product of p square, which is p mu, which is the product of this 4 momenta, which is G mu nu P nu in a sense, or you can say this is E comma P multiplied or taken an inner product with E comma P, right. So, let us try to write this quantity, what this will be. Can you tell me? This will be simply E square minus P square. Now, why E square minus P square? Remember, this G mu nu has this 1 minus 1 minus 1 minus 1. So, whenever a contravariant, so for example, if P mu is E comma P, then P mu with Lorentz index sitting here, that will be simply E comma minus P, and that is precisely the reason that we have E square minus P square. Now, what is E square minus P square? You remember E square equal to P square C square plus m naught square C to the power 4, and if I drop the C in our natural unit convention, this is simply P square plus m 0 square. And what is E square minus P vector square? This is simply m square, right, or m 0 square. So, this is m 0 square, and this is a scalar. So, this remains invariant. Okay. So, P square is invariant. Now, there are not only scalars and vectors, but you can also define tensors, say for example. So, here there is one example of tensor that I am actually defining, which is called T bar alpha beta. How it will be transforming from T mu nu, that will be basically del x bar alpha, del x mu, del x bar beta, del x nu, T mu nu, where you see that mu and nu are the repeated indices which are summed over, alpha beta are the free indices which are sitting over. So, can we write it in the terms of Lorentz transformation matrix? The answer is yes, we can. So, this is for example, del x bar alpha del x mu is a Lorentz transformation. So, this is lambda alpha mu and this is lambda beta nu with T mu nu, correct? Now, the number of indices, therefore, you see that plays a very important role, and this provide which you call the rank of a tensor. So, for example, T bar alpha beta, this is a tensor with two different independent indices, and this can be a tensor of rank 2. In a sense, you can also say that the vectors are nothing but tensors of rank 1, and this can be generalized to arbitrary number of indices, and therefore, you can have rank 3, rank 4 and so on. There is an interesting example which we come across in particle physics, which is called the Kronecker delta symbol, and this is a second rank tensor with indices del I and j. So, this is what is called delta ij. Now, can I try to write the Kronecker delta in S bar frame? So, let us write it like delta bar ij, and let us have the delta k L to be denoted for the untransformed ones. So, now can we try to write this transformation? So, first of all, we see that there is an I index sitting up. So, therefore, this will be delta x bar I, and we must actually account for this k, which is a dummy index. So, I will write del x k here, okay. And on the other hand, I have del x, you know, I have j index sitting down. So, I will say del x j sitting here and del x l, which is the L index which is repeated and summed over, and with this L sitting here. So, this is how it actually can be written. And you note here interestingly that this one del x bar del x k, this is actually the Lorentz transformation. This is like lambda I k, but this one is not quite the Lorentz transformation. So, rather this has one contravariant index, one covariant index. So, this is a mixed tensor. Similarly, there is another tensor which is very important and we come across in particle physics, which is called the Levi-Civita and which is called epsilon ijk. It is a completely antisymmetric tensor of rank 3. So, you can try to write the transformation of epsilon ijk also. But with this, let us try to summarize what we are trying to talk about. We are trying to identify objects which remains invariant under Lorentz transformation. Now, when we are saying that there are some things which are kept invariant under Lorentz transformation, you can also say that those are the objects which are symmetric under the Lorentz group. You can actually assign that symmetry transformation to a group also, okay? And it is basically a generalization of rotation group including rotation and boost. Now, let us briefly try to see what exactly do I mean. Let us consider the rotation in a two dimensional plane. Suppose you had the xy and you rotate it by theta and it goes to x bar y bar, okay. How do I write this in terms of theta and xy? Simply this is x bar equal to x cos theta plus y sin theta, whereas y bar will be equal to minus x sin theta plus y cos theta, correct. So, this is something that we all know. So, once again we can rewrite this in the matrix form. So, I can write x bar y bar as a two component column matrix, and similarly I have on the right hand side x y as the two component column matrix, and this 2 cross 2 matrix which is cos theta sin theta minus sin theta cos theta, if you multiply you will basically get back to this previous equation. Or in the component notation very similarly the way that we have been doing, we can say that x bar I, which is the rotated coordinate, will be related to xj by this rotational matrix which is defined by Rij matrices, okay. And what these rotations do? Interestingly, this keeps, for example, in two dimensional rotation, the important property that it keeps invariant is x square plus y square. If you take a 3-dimensional rotation, it keeps x square plus y square plus z square invariant, which is to x prime square, that is x square plus y square plus z square equal to x prime square plus y prime square plus z prime square. This can also be shown via this relation that x bar covariant I, where the repeated indices is summed over. This can be written by this transformation matrix like Rij R transform Ki xj xk, and this basically tells you that this transformed matrix RT will be the inverse of it, that is RTR must be equal to 1, and with that you can actually show that this x bar I xi is equal to xj xj, okay. So, this is actually a group of rotation, and two dimensional rotations are called special orthogonal group, which is called SO2, and the determinant of R will be actually equal to 1. So, that is why this is called the special orthogonal group. Now, I am going to give you a brief of this group theory later. So, this was the rotation. Now, what does the Lorentz transformation do? Lorentz transformations are similar to rotations, but what it does, that instead of keeping just the x square plus y square plus z square invariant, it keeps ct square minus x square minus y square minus z square invariant. Remember, this is the one with which actually we got this transformation on board. So, therefore, the rotation about z axis in one hand leaves x square plus y square invariant, whereas a boost in the z direction leaves the t square minus z square invariant. So, instead of having this sine and cosine theta which defines the rotation matrix, we can actually have sin h, sine hyperbolic and cosine hyperbolic to actually define the Lorentz transformation, where instead of having cos square theta plus sin square theta equal to 1, you have the cos h square beta minus sin h square beta is equal to 1. So, the boosts are similar to rotation, but instead of having this cos theta and sin theta, we can define it by the hyperbolic, sine hyperbolic and cos hyperbolic. In general, we can also say that the Lorentz group is the most general set of transformation which preserves the Minkowski metric, that is lambda t g lambda is equal to g. And we can show that the Lorentz transformation can be written as a product of rotation and boost along x, y or z axis. So, how do you write the rotations along x, y, z axis? This is something that you should actually go back and check, that this is actually along x, this will be cos theta x, sin theta x, cos theta x. For y direction, similarly it will be cos theta y, sin theta y minus sin theta y, cos theta y, where similarly for the z direction, where theta I will be varying between 0 to 2 pi. Now, what will be the boost matrices along x, y, z direction? This will be defined by, as I said, cos hyperbolic beta x and sin hyperbolic beta x, and this is for the rotation along the x or the boost along x. Similarly, along y and z you can write, where this beta I has a limit between minus infinity to plus infinity. This is a nice and small exercise which you can show that this transformation that keeps t square minus x square invariant are the Lorentz transformation. For example, if you have x going to x bar equal to x plus v t by square root of 1 minus v square by c square, or t going to t bar which is equal to t plus v x by c square by square root of 1 minus b square by c square, you can instead write this x bar and t bar in terms of this cos hyperbolic and sin hyperbolic and get precisely this matrices as I have written, where the cos hyperbolic beta x is nothing but 1 by square root of 1 minus v square by c square. We have taken c is equal to 1. So, therefore, the sin hyperbolic should be something like v by square root of 1 minus v square. Okay. So, this relates the boosts with the velocities of these different frames. So, finally, to sum it up, we can say that we can identify different quantities which are Lorentz invariant, and the basic way to do it is to see whether there is an index, Lorentz index, which is actually sitting on it. For example, a scalar field is a Lorentz invariant quantity, but when you take the derivative, it is not, it is rather a vector. A vector field W mu is a Lorentz vector and it is not Lorentz invariant. A tensor, of course, T mu nu that we defined is also not a Lorentz invariant either. It has two different indices, but in principle when we talk about QFT, Lorentz invariance is a guiding principle. The Lagrangian that we write must be Lorentz invariant, because we want to describe same physics in all inertial frames. So, with this I finish today, and basically we will now construct some of the important quantities that are required for particle physics, which are like the cross sections and decay widths, and we discuss also the possibilities of how they are Lorentz invariants and so on. Okay. So, with this I finish today and see you in the next lecture. Thank you.